Hey, we're live? All right. All right. Hi, everyone. Welcome to Kubernetes, 7 lessons learned from 7 data centers in 7 months. Hopefully, you'll find this as interesting as the journey that we took. Click. No? Click. All right. No clicker. All right. I'm Mike Tugeron. I'm a senior site reliability engineer with Adobe. I've been using Kubernetes since around mid-2015.
And I'm Tony Goslin. I'm a site reliability engineer at Adobe, and I've been using Kubernetes since about 2018.
So just a real quick agenda of what we're going to go through. Some of this stuff is going to be process-based. Some of it's going to be technical. So it's a bit of a mix. Hopefully, it's a good balance between the two for everybody. The obligatory marketing slide. Adobe Advertising Cloud allows you to manage video, display, search advertising across traditional TV and digital formats. We're a high traffic, low latency, huge data set business. So that kind of gives you a background of where we're going with our stuff. So our Kubernetes overview, right now we're running around 225 worker nodes. We expect this to grow to 300 over the next month or so. 6 Openstack data centers in 4 different regions, Kubernetes running in each of those. It's kind of our smaller footprint at the moment. We expect most of our growth to be in that area to reach that 300 by the end of the month. We have 3 clusters in AWS, US East 1. Those clusters are primary for machine learning and stats workloads. So there's cluster autoscalers running in there. We got a lot of volatility, scaling up, scaling down for those ML jobs. The way we do deployments is we bake a new image and then we cycle it out to the cluster. This is for both AWS and Openstack, running on top of the Openstack VMs as well. And we do this about every 4 to 6 weeks. So what would a talk be without a demo? I wanted this later in the demo or later in the deck, but it takes too long to run. So right now, we have a cluster in our lab that is still running 1.11.8. It's a little bit out of date. So we want to go ahead and run one, get this upgraded to 13.5. So I'm going to go ahead and run our deployment script here. It's going to install some dependencies. And demo gods be good to me. It should, there we go. Starts doing some health checks on the nodes, starts checking what's there, starts draining the nodes, and then once they're drained, it starts terminating them. All right, so this whole process takes a little while, so we're going to come back and talk about it a little bit more later in the presentation. Our first topic that we want to go over is communication, teamwork, and training. You really can't do good training without good teamwork, and you don't have good teamwork unless you're having good communication. This, to me, is probably the most important lesson that we learned along our journey, and it's probably the most critical things to get right for your journey, so that without them working hand in hand, it makes that process a lot more difficult. So Adobe has some very large engineering teams. Within the Advertising Cloud, we have several hundred people across multiple time zones, geographical locations around the world. And so it's very difficult to reach everybody in the same format. We can email, we can Slack them, we can talk to people in person, but there's always somebody important for that matter, who doesn't read one of those formats. They don't read their email announcements. They don't read the Slack channel. And so we found we really have to shout it from the mountaintops. We have to yell it out, repeat it, rinse and repeat, and that can be really frustrating. But the thing that we learned with it is when there's significant changes to the cluster, be backwards breaking or not, it may just be a change in the way in which it works, the users of this system need to know it. So the onus of the responsibility falls onto the operators of the cluster to make sure that their end users know what's going on. And so one of the things we found most useful is going to key stakeholders, talking to the teams in person, talking through why we're doing these upgrades, why we're doing these changes, how it's going to benefit them, and then just shotgun this out, take the time, do video calls with the people over in India, do instant messaging with the folks in Bucharest, go to the stand-ups that are here that are not here, but in California. So you just got to shout it out. You got to reach everybody on the format that they listen to, and the responsibility falls onto the operators. So within teamwork, a couple months back, we had a bit of a fumble. We have this deploy bot system that applies our YAML changes onto the cluster when engineers get their code into the master repo. Team A wrote this application. Team B was running it. Both teams thought the other team had set up the monitoring. And so what was happening was a third team committed some code, expected it to be applied, their application updated and running now with the new code, and it wasn't. And they were spending hours trying to figure out, well, why aren't my changes there? Why aren't my changes there? And it turned down into that there was a malformed YAML, and the deploy bot just was trying to apply, it couldn't, and it just moved on and nobody knew about it. So this is one of those cases with teamwork where even though somebody else had written the application, the operator team, infrastructure team was able to come in, put in the monitoring, so now that it notifies each individual team according to namespace that, hey, your application failed to deploy, be aware of it. You know, you can get those messages via Slack or PagerDuty or whatever feels comfortable. But we were able to work together as a team to fix each other's stuff to make sure everything goes successfully. You know, you are one company and you want to move away from the throwing things over the wall. Teamwork is what helps you not do that. So with training, there's a balance between abstractions and experts. You got to have the experts who really know how things work, but you don't want every single engineer who's using Kubernetes to have to know the nitty-gritty details of how Kubernetes works. That's not efficient. You know, it's to train this entire room. You know, there's close to 100 people in here on how to be an expert of Kubernetes is going to be a lot more work than training 10 people and having those 10 people create tools that abstract out how to use Kubernetes into a way that removes the boilerplate of deployments, removes the boilerplates of your stateful sets, and makes it easier for you to do your deployments. We found to do this, as we get those experts then go out and pair program with the various teams to help them get onboarded to learn how to use the cluster. But be careful not to abstract to the point where you're no longer using Kubernetes. You don't want to have users using tool XYZ instead of tool Kubernetes. There's no good answer for where that balance is for each team. You kind of have to find that for yourself. But one thing I do strongly believe is that kubectl should not be your primary tool and primary entry point into the cluster. Write tools to abstract that interaction. Make sure log aggregation goes to something like a Splunk, an Elk cluster, Sumo Logic, whoever it happens to be, so that that log aggregation, the querying of those logs is easy to do versus a tailing of the logs across multiple pods that are running. That's just not scalable across dozens or hundreds of pods for the application. Yes. All right, so here's a simplified diagram of our code to production pipeline. This is pretty generic looking. Everybody has their own steps to insert somewhere into this chart. This is probably the second most important thing to get right with inside your journey. We've had problems where at one point it was a little clunky. Our build times hit 20 minutes instead of the minute we were targeting. And as these problems happen, people don't adopt it. They go around it. They create their own way of getting their code into production. And all of a sudden you've lost your efficiency of scale of having a pipeline that makes it easy to get your code from your workstation into your staging or development environments, into the master Git repo, into production, all along the ways with everything there. You don't want people side running that process. You want the process to basically say, people say, that's it, that's all I have to do, and all you have to say is yes to get there. So part of our journey with this code to production, we also have, there's tools out there that can help get you there. Helm, be it just with Tiller or using the templating features for getting to GitOps. Customize, Capitan, Ship, Caseonet, there's dozens of them out there. Pick and choose your poison, what works well for you or not. For us, we found Helm templating works really well for GitOps workflow. It works really well for third-party tools, so we use that inside of our infrastructure team. There's a lot of good open source stuff there. But we found our application team didn't need a full templating language, full set of functionality that Helm provided in order to do their work. We actually found for a lot of the engineers, it was more complicated and harder to pick up than just using something like a customize where they just override the attributes of how many resources they need depending on what environment they're deploying to. So there's nothing wrong with using multiples of them. And we're also looking into the whole idea of applying customize on top of the Helm rendered templates. So I mentioned GitOps. It is an overloaded term. It does mean a lot of different things to different people. For us, it basically means that once code is in master, it goes to production. And what's running in production is what's in master. That may seem like, yeah, that's what you do, but there's tooling around this to make sure that your build platform builds the artifacts in your containers at the right step. Does it build it post-master? Well, if it does that, then what's in master is not necessarily what's in production. So some of the builds have to come back to the PR stage, where it goes, when the PR is created, the code reviews, the containers are built by your build pipeline then. So when the YAML and the container names get into the master trunk, it's out there. It also means that there's the reverse check, that what's running is kept in sync with there, making sure that nobody's gone in and modified the running code in production, modified the pods there. What's in master is constantly reapplied back to make sure that it keeps in that same thing there. So one of the troubles we had with this is we are also moving from a polyrepo setup to a monorepo. I'm sure if we were to poll this audience, we would get 3 different types of opinions on which is the proper way to go. We've had a lot of debate inside for us, but what we did find was going to the monorepo did allow us to do the GitOps process a lot easier. But the lesson that came from this is it's a lot to do. It raises the barrier of entry into the Kubernetes system of how to get onto there. So try to make sure your shifts from one way of doing code to another doesn't overwhelm your engineering teams so they're just not able to get the job done. It takes them weeks instead of days to get onboarded. So there were some ABCs of production usage that we found people had trouble with. The first one, the horizontal pod autoscaler. Lots of people already know you can easily scale that on CPU or memory, but don't always know that you can scale on things like HTTP requests from your ingress controllers. You can also install plugins that allow you to do things like pulling metrics from Prometheus to do custom auto-scaling actions. A common use case for that is you have a job queue. When the queue reaches a certain size, you need to launch more workers in order to handle that extra load so that you don't wait forever for that job queue to be processing. Those metrics can come from Prometheus, hits the metrics API server. All of a sudden, your deployment now scales based upon that. It's really powerful. One of the gotchas we had with this is we used to set our number of replicas inside of our deployments. Our deployment would say we want 3 replicas because that's our minimum. But our HPA would say we want between 3 and a dozen, right? And if it had scaled up to 10, next time that deployment had been applied with 3 because perhaps there's a new version of the code, it would scale back down to 3, then back up to 10. So if you're using the horizontal pod autoscaler, don't set your deployment replicas, set it all in the HPA. That way there, if there's 10 running, the deployment will apply against those 10 pods, not shrink you back down. That was a gotcha that hit one of our stats teams when they switched, because originally they were using a fixed number. They went to the scaling and kept trying to figure out why it brought them back down. Pod disruption budget's something that's been really overlooked for quite a while on our teams. This is different than the replicas and the deployment strategies that you may, the deployment strategy inside of a deployment where you say, oh, I don't want more than 10% of my pods offline while I'm doing the deployment. That's not what a pod disruption budget interacts with. Pod disruption budget is more when Kubernetes does its rescheduling. So let's say that you're draining your nodes in order to do a deployment. You're moving workloads over to another system. You don't want to lose your quorum of etcd, right? You run a 3-pod cluster of etcd, you only want one of those offline at a time. That's where pod disruption budget comes into play. If there's 2 nodes being drained and 2 of your copies are on there, Kubernetes will make sure that it doesn't move both of them at the same time. It moves one, waits for it to become in the ready state, then moves the rest. This doesn't apply, though, as some of our teams learned, to manual deletions. If you do a kubectl delete to a pod and you do it to 2 of those 3 etcd nodes, it'll take them both down at once. The pod disruption budget isn't respected for those manual actions. But this is great. If nodes go down, workloads are happening, your application stays up. It's not just a change like happens in deployments when you're doing deployments. This is for the life cycle that it's running inside of the cluster. So we also, as part of going to production, started using DevOps. There's expertise and specialists on both sides of the board, within the ops side and the engineering side of the house, and DevOps brings it together DevOps also brings that empowerment and that speed, but because the expertise used to be on one side of the house or the other side, and realms of responsibilities are shifting, things get lost in the shuffle. You may see up here that we requested 1,000 cores for the cluster, but we're only using 32 cores. That's a bit of a gotcha, right? That's a very over-provisioned Kubernetes cluster that's supposed to be auto-scaling. So we had engineering teams requesting a lot more CPU than their application actually used. So we didn't have a guardrail in place to make sure that what you're requesting is what you're actually using. So now we have some reporting in place that says, hey, you're requesting 8 cores per pod, 10 pods, that's 80 cores you're requesting, but you're only using 4 overall. Does your application really need to use that? Should you set your requests lower and a higher limit? Or should you have everything being lower because your application just straight up doesn't need it? So guardrails help protect both the infrastructure and operator side of things as well as the engineering side. You know, it's got budget considerations. It's got guardrails for just making sure pod disruption budgets are in play. If you don't have those, then you know that there's going to be something potentially wrong with your application through the entire life cycle, day 2 of it. So we were doing a cluster upgrade. Let's see how that has gotten. All right, it's still doing its checks. It hasn't done the last node yet. So let's keep going and we'll talk about it and come back to it later. But if you're like us, you can't double the size of your data center on a whim because you want to do an upgrade. And most likely you're also like us where you don't run at less than 50% capacity. So blue-green deployments of Kubernetes can be very difficult. It's also very difficult for the application teams to balance their workloads across multiple clusters because that's not just balancing your workloads and doing load balancing. It's essentially running in 2 separate clouds because Kubernetes is a cloud. So that's a challenge for the application teams. So then you start talking about canaries where, hey, I'm running n number of nodes of a new configuration or a new version within the other worker nodes that are part of the cluster. And that works really well because then you can do some comparisons there. But one of the problems we're having is the proper visibility and observability into the cluster to do those comparisons. Because you can't just compare like old school VMs where you're upgrading, they're not that old school, but you can't compare CPU, memory, disk usage between the old nodes and the new nodes because your workloads are going to be different. It could be any workload. It could be scheduled workload in the middle of your monitoring periods. So you start having to deal with the observability of how to kubelet error messages perhaps, or kubelet performance, API server calls for those nodes versus other nodes. And it becomes a lot more difficult to know whether or not that canary is successful or not. So this is a challenge we're still working through. We have some metric comparisons. You can see in the deployment here of the masters. We're checking, make sure etcd is coming up healthy before moving on to the next one. We have a bunch of pods and kube system that we're checking. And so we're kind of checking as we go with these deployments that everything keeps its state healthy. You can't just say, all my masters are upgraded and we're good to go. So, all right.
So lesson 4, multi-cloud challenges. Adobe Advertising Cloud lives in 2 different clouds today. AWS is where we run most of our persistent workloads. So things like Kafka, Aerospike, other workloads that require long-term persistent data storage. We basically use USEs for AWS, kind of like a data warehouse. And then for our data processing, for actual bidding and advertising analytics, we run those in 6 Openstack locations or regions around the world. We're running about 150,000 cores of OpenStack for that architecture. And these are more kind of ephemeral things. Basically, they receive data in for about what kind of data processing they're supposed to do. They do the job. And then they return the long-term information we care about back to US East. So we care much less about persistent workloads, or persistent storage, rather, in these regions. And this has worked great for us. It's been really a money saver for us. When we made the transition in 2014, we were able to cut AWS costs for that particular kind of compute in half, in some places into a third. It's been wonderful. And it's all the bad. Preaching to the choir here, the benefits of running your own private cloud. And when we built this, we kind of took the mantra of build what you need. We went through several iterations of building our own private cloud, some where we tried to build all the different pieces. And then what we realized along the way was you only need to build what you need. So we focused on 2 projects. We focused on Nova and Neutron. We care about fast compute and low latency network. That's it. So all of our OpenStack workers or nodes are basically, they're all local storage. We deploy at a rack at a time. And then again, this is to design a system that is reliable, consistent, and durable, and cheap. So suddenly, about a year and a half ago, Kubernetes happened. Our engineering team came to us and said, hey, we're looking to make the CI/CD journey here. Part of that is containers. We need to start thinking about running Kubernetes in the places where we've been running our virtual machines, so AWS and OpenStack. And we said, great, can you give us $20 million for new data centers? We didn't get that. So what we decided to do then was to start deploying first in AWS, because AWS we knew we could get up quickly. It was where a lot of the development work was being done. So as we said, we deployed our 3 clusters there. And our machine learning folks are using it for production as well, because they were using their virtual machines in AWS for production as well. So we were able to design this, and we really tried to focus on designing this in a modular way. Then came phase 2. We started focusing on OpenStack. And how are we going to build the same kind of user experience for Kubernetes on OpenStack? And again, with OpenStack, we had a couple of challenges here. We had no persistent storage. So moving things like persistent volume claims, these all of a sudden become challenges. We had no autoscaling in the way that we configured OpenStack. So that wasn't available to us as well. We had to kind of design, think about that as we moved workloads around. And then finally, we also had to think about compute and rack anti-infinity. When you put things into public cloud, that's, when it's in AWS, it's Jeff Bezos' problem. Whether you have noisy neighbors or whatnot, they kind of handle where your VM is, where your workload is, and make sure that it's in a place where it's getting the resources that are allocated. When it's in your private cloud, that's our problem. That's the operator's problem. We need to make sure that our workloads are spread out equally. We need to make sure that quorum won't be broken if you have a piece of compute that goes down, or if you have a small network failure that divides the system. You need to make sure that you're actually taking this into account. So how do we approach this? The first thing we did, and this started with the AWS build, is we made sure that we were as modular as possible in our design. We try to keep one code base for all clouds, and then basically where there are branches, or where there are differences, we build modules out, and basically when we target different clouds, we pull those modules in so that we can do that. And the advantage of this is that we're, again, giving a consistent experience for our users, our engineers. We want to make sure that things that when we apply fixes, that they go across all clusters, that when we apply new features, that they go across all clusters that are applicable. And this keeps us honest to make sure that we're designing for both. And part of the way that we did this is we made sure that we have labs in all of our clusters. Now, you might think that when you're developing for Kubernetes, you might go ahead and say, yeah, we'll just have one lab, we'll develop there, and we'll push to prod for all clouds. Even if you're taking this modular approach, you still really need to have a lab that's just for your operators to test out all these changes, to make sure that they actually work in all clouds. It's very important. Sometimes that's an argument that's hard to make. You don't want to take up compute and have that budget argument, but it's a mandatory thing. You must have that. You must make sure that you're testing in all environments. Finally, for rack anti-affinity, we weren't able to find a third-party solution for this. We were lucky, though, that we had a member of our team who was also trying to solve a similar problem that he had in parallel. We were able to leverage our tool called Osaya, which is the OpenStack Simple Inventory API. It was written by a member of our team, Mikola Malayenko, who's sitting right front here in the black hat. You can ask him questions about this. Basically, it's a simple RESTful API that you can use and basically pull information at the hypervisor level, at the compute level, at the rack level. You can basically pull in attributes about your workload that's running on OpenStack. And the way we leverage this in Kubernetes is that we're actually able to tag our pods with this information. So when we look at a pod, we can actually label it with the hypervisor it's running on, the actual compute it's running on, the rack it's at. And by that, we can actually build rules that help us set up anti-affinity to make sure that we don't have all of our Elasticsearch running on one hypervisor. And this has been really helpful for us. Obviously, not everyone may have someone who's going to be in-house to write this. I'm very proud to announce that Adobe is looking to open source this spring. If you have any questions about Osaya, you can see Mikola. Again, he sits right up front here in the black hat and the blue shirt. He loves talking about it. He's also very bald. Just throwing that out there. Lesson 5, knowing your application. This seems pretty obvious. We're operators. We know our applications. If you haven't run Kubernetes before, the gist of what we're trying to get to here is that Kubernetes brings advantages. There are lots of talks here that will probably talk about that. But it also brings, it operates in a different way than we're used to in terms of bare metal or virtualized infrastructure. And you need to kind of make yourself aware of those changes and think about that in the terms of your applications. Don't just assume that you can just plop your application on Kubernetes and it's just going to work the way it always has. You need to think about things like service discovery. Some of the things that we thought about early on were, does the app need a fixed host name in order to function? Zookeeper, for example. How does the application save its state? Is it on memory or on disk? What about cluster data? Are we sharding data like Elasticsearch, or are we replicating data like MySQL? And how will it handle rescheduling? And rescheduling in this case, with virtual machines, means rebooting. Can you just shut the app off and on again? Does it need some pre and post operations there to make sure that it's going to operate properly? So these are the kind of considerations you need to have when you deploy something. And also, you need to make sure that your developers as well are aware of this too. That, again, they can't just take what they built in virtual machines, just plop it into a container, and then we're off to the bars. How many people have run Elasticsearch or know about Elasticsearch? Raise your hand. A lot of people, right? Me too. So we, early on in the Kubernetes process, we had to bring up an Elasticsearch cluster. So we did what probably a lot of people would do. We went online and we found a blog with a how-to. And we kind of took what the person wrote at face value, and we deployed our Kubernetes cluster, our Elasticsearch cluster in Kubernetes. And it looked pretty much like this. We have our clients, our data, and our master servers. We had an ingress API set up. We had our data on persistent volumes. Everything worked. It was great. We were really happy. Jira ticket closed. Great. And then about a week or two later, we had to go ahead and update our nodes in the development cluster. And the way we were doing that at the time was we would take a worker node one at a time. We would drain it, so we'd move all the pods off. They'd go get scheduled in other pods. Then we'd remove the node, and then Autoscaler would just bring up another node for us with a new image. Great. About halfway through the process, we found this. This is not something you want to see in Elasticsearch, for those of you who don't run Elasticsearch. This is all bad stuff. Basically, all of our nodes for Elasticsearch, clients, master, data, they had all crashed. We had a lot of primary and replica shards that were unassigned, which means they just weren't anywhere. And you can see once we recovered here, if you look down at the bottom here, we had 93% active shards in our cluster, which means we lost 7% of our data. This, again, was in our development cluster, so it was a great lesson to learn early on in dev. But still, this could have been pretty bad. And the reason we got into this place is because, again, we didn't think about our application. We didn't think about, gosh, how is this going to work in Kubernetes? What kind of resiliency do I need to think about? And how is it going to work with scheduling? So here's what we did to fix the problem. This is the way we're running it now. The main changes that we made here was we added pod disruption budgets to make sure that, as Chuj was talking about, that we make sure that we're respecting quorum when we're taking things in and out. We also made sure we have pre and post operations here so that when we're removing, say, a data node, that it tells the rest of the cluster, hey, I'm going away. And then when it comes back, it says, hey, I'm here. Give me some data. Start sharing with me again. And giving this, setting things up like this gave us a lot more stabilities. Things now when we're actually running deployments, they run correctly. Some other changes that we made to our worker deployments in general was to make sure that we were respecting pod disruption budgets for a longer period of time. What we had originally was we would drain and just move on to the next. And sometimes we need to make sure that we drain and make sure that everything is really actually drained and it's disappeared. Some other things we do is we pre-cordon nodes. So we make sure that things aren't being scheduled on nodes that we're planning to replace. And then we also make sure, another trick we've been using is actually turning off our autoscaler and then doubling the size of our cluster, at least in AWS. And the reason for this is then we make sure that we're bringing up all new images for our workers, and then we move our workloads once. So rather than flapping our workloads over and over, having them bounce all over the place, we do it once, and then we take down the old workers, and we're done. That obviously doesn't apply to Openstack, but we'll get to that in a little bit. Now, knowing your application, you don't have to know every little thing about your application, and you don't have to be a Kubernetes master either. There are, fortunately, resources that can help you here. For example, we use Helm. We use Helm because as operators, we run a lot of third-party infrastructure. And a lot of third-party infrastructure have figured out that a lot of people are running their applications in Kubernetes, and they're writing their own Helm charts. So basically, they're writing a best practices guide for how to run your applications. You don't have to write it yourself and get it wrong and figure it out and reiterate. Someone's already done the work. So if someone's already done the work, you can use their work. And if it doesn't quite meet your business case, it at least gives you a starting point where you can then extend off their chart and write your own. So for example, with a lot of our charts, we start with Helm charts, and then we extend off those and add our own RBAC rules. But with everything else, how the application actually runs, that's already handled for us. And it also gives you a good upgrade path in terms of when the next upgrade comes out, you're not having to write that YAML from scratch, thinking about new attributes that have all of a sudden been added to the application that you now need to consider. Metrics-based monitoring. So this tweet, my boss found last week and posted on Slack, and we all thought it was pretty funny, but it really kind of nails home what we learned in terms of writing monitoring that's applicable to Kubernetes. So, I mean, everyone can read, but yeah, Kubernetes pods are mortal. They are born, and when they die, that's it, they're done. It's different than bare metal and virtualized infrastructure. When your VM goes down or if it freezes up, restart it. Then you can look at the logs, see what happened, you can do some post-mortem. Same with bare metal. With pods are gonna go up and down all the time. And it may not be system failure, it may just be bin packing. Hey, there's more capacity over there, I'm gonna shift some workloads over. Shut it down here, bring it up there. That means just targeting the pod like you would a bare metal node or virtualized infrastructure. You can't just port your monitoring over and have it work the same way. So you need to think about it a little differently. You need to think more at the application level. So, we think more about deltas and patterns. If you start collecting metrics and also encouraging your application developers to provide metrics, very important as well. So they're exposed to things like Prometheus. You can then start running monitoring that basically looks more at trends and deltas rather than actually specific events. And that's not to say we don't care about events. If your post goes down or your service goes down, you care. You want to get paged, like Touche probably was right there.
Yes.
Yeah, cool.
And that's because I forgot to turn off alerting before doing that upgrade.
Oh, you can't time it any better than that, guys. You can't. Awesome. One of the places, a couple of the examples that we had with metrics-based monitoring, we use it for resource requests versus actual usage. We can actually monitor on that, flag people, as Touche was talking about before. We had an issue a while back with machine learning. They were having periodic degradation in performance. And because we were monitoring back at the worker node level, with disk performance and then being able to tie that around to where workloads were at the time, we were able to actually pin it down to be actually specific volumes that were being used for transient data processing. And another thing is volume utilization. We have alarms that are set up not to say, hey, your disk is at 90%. We have it saying, hey, this disk, based on previous trends, is going to fill in 3 days. It's a much better way to kind of approach monitoring as opposed to just specific point in times like, oh my gosh, this happened, react. And again, collecting metrics, you need to do this for everything. And you need to apply monitoring for everything. And even if it's the simplest application where you're like, I know this application, I know if it goes down, it doesn't impact anything. Having all your metrics in one place, it makes it a lot easier to start correlating behavior around how applications interact, be it network traffic or disk usage or CPU or just inter-application interaction in general. The more information you have, the more you can actually figure this out. Because again, it's going to be a lot harder to jump in and just tail a log on various servers or pods. And next we have autoscaling benefits.
All right, so before we hop into this, let's take a look at the deployment. It should be finished by now. Ooh, hey, we got a failure here. Yay.
Uh-oh. Wah, wah.
As part of the checks, deploybot is not ready. Well, that's a problem. But the thing is we were monitoring the entire process as we went along, and something didn't work, and it let us know. In this particular case, a deploybot is a decent one to not have going because we don't need to do deployments during an upgrade. That should have been still a problem that we would need to fix as soon as we're done here. But if you look, our masters are now upgraded to 1.13.5. So that's a good thing. You'll also see in here that we were checking other things, Cert Manager, a custom app we have, the dashboard, DNS, all sorts of stuff. So with the metrics monitoring, we do still check for events because sometimes that is just as critical as the trends. So talking about autoscaling, it's really great in AWS because we're able to get some cost benefits there. It also, we don't run 20 worker nodes for our ML workloads that only happen between midnight and 2 a.m. It shrinks down, goes back up, and it's great. It also, ooh, typo, darn it. Easier auto-remediation. So when something goes wrong with a worker node, all we gotta do is just have a process that grabs all the logs, different metrics about the system, ships it off to a bucket, and then we just kill the node, and it just comes right back up. These are great things to have happen. We don't have to get paged or alerted when things don't go well. But that does mean that there's more frequent rescheduling of applications. And so we were running into a problem with one of our stats workloads where when autoscaling happened, it took 2 minutes for their application to come back online. And why was that? It's because in AWS, sometimes it takes a little bit of time for one volume to move from one host to another host. There's the pager still going off because deploybot's down. But anyway, so moving around. So you got to think about those sort of challenges of not just how does the pod move, because usually a new pod comes up within a couple of seconds. What's the impact of this autoscaling event on the application performance, not just the Kubernetes performance? So we're looking at making a few adjustments for this. We are using the immutable images as we were talking about, and those are for things like API server, kubelet, Docker. And there's processes like kube, proxy, calico. Those are going through the GitOps process we had talked about. And this has been working great in AWS where we have persistent storage, but it's not so easy to use and more difficult inside of our Openstack data centers. So we're exploring some light configuration management to reduce this scope. So if we're just making a minor change to our kubelet configuration, we're looking at applying this via config management approach versus cycling the entire cluster. We still want to bake that image so that as autoscaling happens or new nodes are deployed, nodes are replaced, they come up with those changes already in place so that as one of the first things that happens is Kubernetes is able to serve traffic right away instead of waiting for configuration changes. But it does reduce the churn and does reduce the impact upon our applications to be able to just restart kubelet instead of replacing the node. So, off by one errors, let's take a deep breath. I talk too fast and don't always take a deep breath. But we're all one team at Adobe, so we learn and fix these things together. The operation team can help the engineering team with patches. The engineering team can make patches to the Kubernetes infrastructure. So we learn and fix these problems as we go along. It's been an enlightening and fun experience. Everybody loves working with Kubernetes. We talked about challenges throughout here, but we also had a ton of success. Our dev to production lifecycle is fast. People are able to get things up once they're code complete to production in a matter of hours, not days. New systems go live within hours, not weeks. And man, everybody is just super happy about it. I don't know anybody who hasn't just said, that's all I got to do. This is wonderful. So just remember in your journey, as there's problems, it still can be successful even with major problems. And come back, take that deep breath, and know that it's going to be successful in the end. So I know we're close to out of time, but thank you very much. Are there any questions people have? Here's our contact information, where the slides are at. I'll try to fix that typo.
Hey, thanks. It was a nice session. Couple of questions. Did you use service type with load balancer on premises in OpenStack, and what did you use for that? And did you consider Cinder for storage provisioning in OpenStack?
So for load balancing, we have a series of nodes that are worker nodes that are dedicated to load balancing. So we're using some DNS trickery for health checks to bring the IPs in and out of the DNS record. Comes in and then uses the Nginx ingress to distribute. It's just round robin DNS essentially, and then distributes out. That's how we're doing it for internal, for things inside of our data center that are trying to access the cluster, for internal, but inside and outside of the cluster. For coming in from the internet, we're using the same ingress to the data center that we are for both Kubernetes and our VM-based applications, which is a series of high-performance bare metal HA proxy servers. The second half of your question, Cinder, like Tony had mentioned, we have a very vanilla, high-performance OpenStack installation with just compute and networking. And right now we're going through trying to figure out what to do about persistent storage, because it's in a Kubernetes world, it's becoming more important because a restart isn't just an app restart, it isn't just a VM reboot. The data moves somewhere else and data gets lost. So persistent storage is becoming more important.
So I have one question. So since you transitioned over from OpenStack world to Kubernetes world, did you have to modify any of your applications because of the dependence in terms of how the applications get initialized and whatnot? Because in the pods, they can come and go at a different times.
Absolutely. I mean, we haven't so much because we're more on the infrastructure side, but our developers, absolutely. That's been one of the kind of hardest lessons to learn, that you can't just forklift your applications and put them in containers and we're done, awesome. You have to think in a Kubernetes operational model, how it operates there and how to leverage those benefits.
Yeah. Your question,
Yes.
sir?
Hey, thanks very much for that. A little off topic, I heard you mention persistent storage and Kafka in the same sentence. Are you just letting your topics just grow and grow and grow? Or do you have some kind of offload thing for that? Or have I just completely misinterpreted what you said?
We don't have Kafka running in Kubernetes yet.
A
team is working on that. I don't know enough about how they're using Kafka to really answer your question. I do know they're one of the teams that are saying, hey, we need some form of persistent storage before we can run in the data center.
Yeah, that's one of the milestones that we still need to hit here. Either we figure out the persistent storage problem that we have where it doesn't exist, or we've got to look at how we deploy that application. It might mean increased clustering. It might mean just kind of figuring, or pinning pods to particular hypervisors. But yeah, that's something we haven't solved yet.
All right, so first of all, that is an awesome T-shirt.
Oh, thank you.
Basically the same one at home.
I knew somebody would get it.
My question is, you kind of lightly touched on some DNS trickery you're doing with the ingress controllers. Could you expand on that a little?
So even though we're in the data center, we're leveraging Route 53 for the DNS. And so we basically, on the load balancer nodes, we have a cron job that's just constantly running, that's reporting back as healthy. It does checks, is kubelet up, is Docker up, is the port responding to just basic health requests, because all those other things could be up, but the container isn't responding for Nginx ingress, that kind of things. And we're reporting it up to CloudWatch. And then utilizing the CloudWatch metrics, we're using the Route 53 DNS health checks. And so that does health checks against those CloudWatch metrics, which then takes the DNS records in and out. And we have a very short TTL. We are taking a bit of a hit because of the DNS lookups all the time. But for us, it was the easiest way to get into to have that inter data center communication for in the cluster, out of the cluster. Eventually, everything will be in the cluster, or hopefully everything. And at that point, those will end up just going away.
By the way, you mentioned that you use Customize for some of your applications, and as far as I remember, there was such interesting problem that when you kind of use config maps, generators, and secret generators, Customize appends some kind of hash, and when you change your config map or secret, a new one will be generated with a new hash, and then you apply this YAML that Customize produces, and old config maps and secrets remain there. As far as last time I checked, this kind of GC problem was not solved. How do you solve this problem of accumulating config maps, secrets, and stuff like that?
Using that hash is actually something new for us. We've only been using that part of that hashing functionality in the last 3 or 4 weeks. Before, we were using other approaches to notify the application that the config has changed and for it to do kind of a SIG-hop reload of that configuration. So we don't have a good answer for that yet, but as part of our deploy bot process that already makes sure that what's running really matches what's in Git, we'll at some point start doing that sort of reverse thing too, where something is running or exists that's not matched to something that's in master.
Okay, thank
So
you.
there's a tool you were looking at. I can't remember the name that does that cleanup.
Yes. We'll put a link to it in the slides when we post those online. But basically, it runs like the reverse of deploy bot. Basically, it looks at the head revision of your repo, and it compares to what's actually in the API server. And if it finds stuff in the API server that doesn't exist in the head repo or the head revision of your repo, it takes it out.
How is this project called?
Trying to remember.
I'm trying to remember off the top of my head.
okay.
I'm sorry.
Okay.
I pushed everything out for this talk.
Okay, thank you. Thanks.
Cool.
Any other questions? Our contact information's up there. Feel free to hit us up if you have any additional questions or want to know anything more. But thank you very much, everyone.
Thank you very much.